So in the previous lecture, we were talking about the recap of computer and their components, and then we have seen the overall implementation of the CPU data path. In that, today we are going to talk about the major topic of your the memory which is used for your data path is the register files. So let me just recall you in the overview of the implementation. So to implement the data path, to implement the data path, to implement the data path for your different class of instructions like your memory reference that covers your load and your store instructions, and the second one is the arithmetic and logic operations, which covers like your addition, your subtraction, your AND operation, your OR operation, and your set less than then. And the third one is your branch instruction class. So in this branch instruction class, you will find the branch equal to and the jump instruction. Okay. So to implement these what are the different hardware components are required means we have seen in the instruction implementation that there are 5 phases. That is, one is your instruction fetching phase. Second one is your instruction decode phase, the instruction implementation. Your third one is your execution phase. And your fourth one is your memory allocation phase, and fifth one is your write back phase or the write back stages. So the instruction implementation happened with these 5 stages. Okay, so when this implementation is happening, the data should be provided, and how that data is takes place from your instruction phase to your decoding phase, from decoding phase to execution phase, and execution phase to your memory, and memory to your write back phase. So in all these cases, what are the different components involved in the instruction execution stage or in the what you call data path stage? First and foremost one is your program counter. So we know that the program counter is used to hold the address of your next instruction. Address of your next instruction. Right? So the output of, and then another component is your instruction memory. Okay? In the instruction memory, it holds the instructions. It holds the instructions. Okay, so that instruction, we know that the instruction we write in terms of opcode and the operands. There are 2 parts in the instruction, right? So that is, suppose if we have the arithmetic and logic instruction, suppose add your R1, R2, and R3. So it says that, this is your opcode and this is your operands. So this complete thing written in terms of 0, 1, 0, 1, 1, 0, 0, 1, suppose for add. And for R1, we know how to write this in binary form using 3 bits like 0, 0, 1 because the number is 1. And R2, we can write 0, 1, 0 because it is identified with the 2 identification. R3 identified with the 3, so we can write 0, 1, 1. So this entire, the binary instruction will store in the instruction memory. That is what we observed in instruction set architecture, instruction implementation part with the example also. Right? So this is first component is PC, second component is your instruction memory, third component is the memory. We use the General purpose register for performing any arithmetic and logic operations, we call that as your registers. So this register, we call, these registers will be there in the register file. So register file consists of your registers, like they are represented with, R1, your R2, your R3, R4, and so up to, if it is using 16-bit, then the R16 will be there. If it is using the 32 bits, then it will use the general purpose register up to R32. So this entire one is selected as your register file. Selected as your register file. So that is the another component for implementing the data path, that is register file. And another memory will be there, that memory we call the data memory. So this data memory, when this branch instructions and the memory reference instructions are implementing, in that case the data memory will be used. The data memory will be used. So here you can see that data memory unit is different from your instruction memory. Data memory unit is different from your instruction memory, right? So in this case, now let us see how these lines are, explains how the data is transferred. So the output of your program counter in data path implementation, the output of your program counter is the address of your next instruction, right? That is given as an input to instruction memory. Instruction memory, that is the address. Okay. So upon receiving this address by the instruction memory, the particular instruction in this address will be selected, and that will give it as an output of your instruction memory. So the instruction is the output of your instruction memory. So in that instruction, you are having the operation code as well as your registers, right? So the output of this instruction is decoded here, and that decoded instruction is giving that there are three, the memories are there, registers are there. So those register names are identified, that your first source for this operation is R2. So R2 will be identified. Okay, that is given as an input to your register file. Second operand is your R3. Second operand is your R3. So R3 will be given. Then the result is storing in R1. Result is storing in R1. So that is your destination, we call. So these registers will be given as an input to your register file. So in this register file, these registers are identified, right? So then the output of this, so this is these three the decoded from the instruction, and these three registers are identified. Okay, that is the read operation. The given as an address of this R1, R2, R3. Next, the output of your register file, is the operands, the values of your R1, So output of your register file is given as an input to your ALU, given as an input to your arithmetic and logic unit. Arithmetic and logic unit is having two inputs. Okay, it takes source one. It takes source one, and your the second one is your source 2, source 1 and source 2. So source 1 comes from your register. So we know that the arithmetic operations, they follows register to register instruction. That means both the operands, both the inputs of your ALU comes from register only. So the output of this register file, the first source 1 means your R2 will come as an input to your ALU, and R3 comes from this source file as an input to your ALU. And then the arithmetic and logic unit performs the operation and gives the output. So that output will be go and store in R1 only in this example. So that result will go and store in the R1. R1. So what is the result? The result of your ALU is the data value. Result of ALU is data value. So that data value will be given as an input to your register file. So that data value will store in which register? In the instruction. When the instruction is decoded, R1 is identified as a destination. So this data value go and store in the R1. In the R1. Okay. And in other case, the output of your ALU is also given as an input to your data memory. Input to your data memory, right? And that data memory is having two inputs here. One is address, another one is the data. So what is the address? When this ALU is performing the operations of your memory reference, that is load and store, or your branch instructions, in that case this data memory is activated and it takes two inputs, one input from ALU and one input from this what you call from the register file. So from this register file, it comes, the output of your register file is in the form of data, the values. Okay. So the value comes from your register file and address comes from this file. So for example, for any instruction like move instruction, move, that is for store purpose, move R1 with your some address R1 with the address, suppose you are having the R3 plus suppose some 100. Okay, so that the address will be stored here, that calculation will be stored, right? So this is the first one. And we know that when program counter gives an address to your instruction register, it also look for the next instruction address. So for that, the current address will be given as an input to the adder, and it will add 4 bytes to find the address of your next instruction. So as soon as the current instruction is executed successfully, decoded and executed successfully, when it is decoded, then your program counter will be automatically incremented for the address of your next instruction by adding 4 bytes. So the adder is used here. So this is the overall implementation of the data path. Let us see how exactly it happens inside this the computer. Let me recall what are the basic operations that happens on the register component in the register file. Okay, so that is, the register is having 4 inputs. Register is having 4 inputs and 2 outputs. So what are the 4 inputs? The 4 inputs, it takes these registers takes the parallel lines. So that is your 32 bits of your registers, 32 bit of your registers. Okay, so this takes 4 inputs. What are those? Register 1, that is your source 1 register, which comes from your instruction. Register 2, that holds the source 2 of your instruction. And write register, the result will be right into the register, that is your destination register. Okay, 3 registers will be identified. Then in this destination, which data should be written? The output of your ALU will be given as an input to your register file. That is, the result of your ALU will go and store into your data. So that is another input to your register. So we call these as your write ports. Okay, so there are 2 read ports. There are 3 input ports, 4 input ports, 2 for your operands, 1 for the destination, and another port is the value of your operand. Value of your ALU result. So what is the output of this register file? Means it reads the data. 1 from your register 1 and 2 from your register 2. That means, suppose if you have the instruction add, we are taking arithmetic and logic unit instruction, arithmetic operations, add R1, your R2 and R3, where your R2 is equal to 5 and your R3 is holding the number, suppose 6. Okay, so then the inputs when this instruction is executed, so your R1, your first operand will be, let me just rewrite it. Okay, so add your R1, R2, your R3, where your R2 is equal to 5 and your R3 is equal to, suppose, 6. Then when this instruction is decoded, okay, so then register 1, that means first operand, that is your R2 will be identified. Second one is your second operand is your R3, and result will store in R1. Okay, so then when this the output of this register file gives that of read data 1. Read data 1 means read the value of your R2. R2 is holding the value 5, so the output is 5 here. And read data 2, that is R3, second operand is register 3, which is holding the value 6, so the output of that one is 6. Okay, and then these read ports, the output of this one will be given as an input to your arithmetic your ALU. It gives, so this input comes and these are given as an input to your ALU. So ALU will perform the addition operation. So how to know this addition operation? ALU will get the instructions from control line, that the operation controls will give the instruction that 0, 0, 1, which is given. So this instruction given, then on these operands it will perform the 5 plus 6, it will perform the addition operation, and the result gives as your 11. So this 11 is a data. So that data will be go and store in the instruction says that the data should go and store in the R1 register. So that will given as an input to your register file. In that register file, it takes the write data, that is 11. Where it should go and write? It should go and write in your register R1, that is destination. So R1 becomes your 11. So this is the operation that happens with this register file. So now, as just explained, the register file is a hardware device that has 2 read ports and 1 write port. Okay, the RF and the ALU together comprise 2 elements that requires to compute the millions of instruction. R format means your arithmetic and logic operations, arithmetic and logic instructions. So that is your arithmetic and logic instructions. That is, we are considering add, your subtraction, or your AND operation, logical operation, OR operation, and your set less than 2 operations. Okay, and then this RF is comprised of set of registers. As said, these registers can be read or written by supplying the register numbers. So that is what we supplied, R1, your R2 and R3 register numbers for read and write operations. From R2 and R3, read operation happens. For R1, the write operation is happening. Right? So in this, the register stored values does not change the state of the register until the read data, until the output will become from the ALU and stored into your register. So however, when this writing to register, the few things need to identify that register number, that is your R1 we identified. Okay, identify the register number, then an authorization bit. Authorization bit means it is giving that if the data is already there in R1, that can be overwrite, that can be overwritten. Okay, that is for authorization bit, and then the clock pulse that controls the writing of the data into teaser. So we have seen in the previous lecture that the clock pulse are given the complete cycle given as the lower one and the upper one cycle is there. So this complete form is known as your the clock cycle, right? This is known as your clock cycle. So in the clock cycle, we have seen that your falling edge, this one, and this one is your rising edge. So when the fall, this is rising edge, okay, your rising edge. Rising edge, when the falling edge is there, that means your read operation happens. In the rising edge is there, that means your your write operation will be there. So this total we called as your the clock cycle or clock pulse. Okay, when down part is the in entire clock, it is divided into two part. If the clock pulse is low, means read operation is happening, high means write operation is happening. Okay, so then comes to the design of your data path for all these the arithmetic logic operations or the class of instructions or your memory reference operations or instructions or your branch instructions. So we'll see the ALU operation or ALU data path design and implementation in detail. So you just recall when performing when executing the instructions, we have divided that instruction execution into 5 stages. So these 5 stages, as we saw in the first stage, the instruction will be fetched. In the second stage, instruction is decoded. In the third stage, the memory is allocated, that is register fetching will be done. And in the next stage, the execution will be done. Okay, the memory execution will be done. And then finally it go for your write back. So see, as we just saw that there are, 3 different class of instructions: ALU operations, memory operations, and control operations. That is your branch operations. For ALU operations, once the registers are fetched, then directly it go for the execution. So your ALU will take the responsibility to execute those operations, and whatever result is coming, that result goes right back into the assigned register. But whereas in memory, as we said before, during this execution, first it calculates the address of the operands first. So for this purpose, we are using the data memory. We saw the last part of your overview of your implementation, that is your data memory unit. The data memory unit will be used for calculating for holding the effective address of your operands, and then from there it goes and access the memory, and the execution will be done by this ALU, and the write back stage will be happen. Whereas in control operations, when the registers are fetched, then it go on. The ALU first calculate the effective address, and that effective address will see whether the branch is completed or incomplete. If the branch is not completed or incomplete, means the same effective address will be used to perform the operations, whether it is memory operation or your ALU operation within that branch, that will be performed. Right? So now let us, we have seen this in the instruction execution phase in the second chapter of our course. So we also see the simple implementation of your 5-stage RISC CPU. You please listen this carefully. This is useful for your assignment 3 as well as for your the examination also. Okay, so in a simple implementation of the 5-stage RISC CPU, we have seen that these instructions will be implemented in 5 stages. That is instruction fetching, instruction decode, instruction execution, your memory access, and write back. So in the instruction fetch, what are the components are involved means first is your program counter, which holds the address of next instruction, and the in memory. Which memory? This is your instruction memory. This is your instruction memory, which holds the instructions. And to calculate the address of the next instruction, the output of your PC is given as an input of your adder, okay, and that will be added with 4 bytes in the sequential address part. So that will give the next program counter address. Next program counter address. Okay. So now in the decode phase, it is going to decode the register fetching. Register fetching in the decode phase. Register fetching means it is identifying which registers are used for operand 1, operand 2, and the result. Okay, and sometimes if you are having the memory address, okay, so sometimes in our example we have seen that R2 plus 1000 in the 1000 where it is the displacement address. In that case, this entire portion becomes your immediate value in the operation. So that immediate value in the form of 16 bits. So to convert that into 32-bit word, we use another component in the instruction decode, that is your sign extend component. Okay, and the components of your execution one is for arithmetic instructions. There is no effective address should be calculated, so your next sequence program counter pass on. But if the memory reference instruction implementation or your branch instruction implementation, in that case the effective addresses will be calculated. To calculate the effective address, these multiplexers are used. And then the actual execution happens in ALU. So the main component of your execution phase is your arithmetic and logic unit. So then the output of your arithmetic of logic unit is given as an input to, okay, given as an input to the memory. Which memory? This is a data memory. This is a data memory. Okay. So these are the basic components of your the 5-stage RISC. So let us see for each line how these are passing. Data is the data path is taking place from your address to the address the PC to your next level for your arithmetic operations. Let us see the arithmetic operation. Right. So first, the output of your address, that is the program counter, is given as an input to your memory, instruction memory, and the same address will be given as an input to your adder. The output of your instruction memory will be given to the next level components, one to your register file. Okay, so that is in our case the add your R1, R2, and R3. So this output of this instruction memory will be given as your source register 1, source register 2, given as an input to your register file. Right? So then the output, because here the source, operand 1, operand 2, and your destination both are registers. All are registers. So this input will be given to your source 1, source 2, as well as your destination will be here itself. Okay, so this destination line, if you observe, this comes from your ALU. Okay, so now output of your register file will be given as an input to your ALU. So two registers. So first one is your register operand 1, second input is your operand 2, and the ALU will perform the operation. The output of this ALU will be given as an input to will be given as an input to your what are called will be given as an input to your write back. So that write back goes and given it input to your register file in ALU. If it is memory one, then that the output of your ALU will be given as an input to your memory instruction. So this is the overall one. Now see the multiplexer one, the multiplexer, the multiplex one, multiplex two, and multiplex three. These are very important. Okay. So this multiplex one is taking an input. Multiplex one is taking two inputs and giving one output, and that output of your multiplex one is given as an input to ALU. So what are these inputs? One input of this multiplex one is your register file input. The output of your register file will be given as an input to multiplex one. Okay. And the second input is the immediate value. The second input is the immediate value, means the memory address. The immediate value of your instruction consists of your memory address. So that memory address is converted from 16-bit to your 32-bit, and that will be given as an input. Okay. So from there, it can select either the operand 2 of your operation is register or immediate. If it is register, then output of multiplex will be register. If the instruction decode says that the instruction decoder giving the address of your second operand, that means your signed extended will be taken as an input and gives output, comes output from your multiplexer and gives an input to your ALU. Similarly, for multiplexer 2, it takes two inputs. One input from your register file and one input from your next sequence program counter. Next sequence program counter. And the output of multiplex is given as your input to your ALU. So now see the output of ALU, the third multiplexer takes the input from the output of your ALU is one input, and the second input is from your next sequence PC. Next sequence PC means the next instruction program counter value. And the output of your multiplexer is given as an input back to your program counter. Now comes to the data memory inputs. This data memory is taking two inputs and one output. What are these two inputs? One input is from your ALU. The output of your ALU is given as an input. This ALU gives the address here, and the second input is the address value which is calculated from here. Okay, the address value which is calculated from here, that is the memory address. Okay, that memory address will be given as an input to your. So this one, the memory address is given as an input to your memory. So that is, this memory address is in the form of your data. So this is the overall implementation of your 5-stage RISC CPU and your data path from your instruction fetching to your memory access. So what are the various components means? PC, instruction, memory, your register files, your signed extended one, that is 16-bit word memory address is converted into 32-bit one, and then the multiplexers takes two inputs and gives one output, and ALU component that takes two inputs and gives one output. Your memory unit, that is data memory unit, takes two inputs and give one output, and another multiplexer that also takes two input and give one output. What are those different inputs means, that we just explain this. So now let us see in this data path. So data path is just a brawn of your processor, as said, since it implements the fetch, decode, and execution cycles in the data path. Okay, so this data path design is to, first what you need to determine the instruction class, whether it is AL instruction or your memory reference instruction or your branch instruction. Okay, and their format in the instruction set architecture, that is the first one. Second, once which instruction is executed is identified, then design the data path components. In data path components, for ALU it requires less components, it just requires only program counter, instruction memory, and your register file along with your ALU. And they all are interconnect, and the interconnection for each of these instruction class or the format, and then compose all those segments, data path segments together, which we identified. This is second phase that will add the composite data path. That composite data path is this part, this entire. So the data path components that includes here, data path component that includes the first is your memory. So that memory is having two memories. One is instruction memory, another one is your data memory. So that is used to store the current instructions, okay, and the current data in that memory if it is address is there. Second component of your data path is program counter set. Okay, that stores the address of your current instruction, and the ALU that is current instruction, and as soon as current instruction is executed, it will store the next instruction address, and the ALU that execute the current instruction which is coming from your memory. So the interconnection of these simple components to form a basic data path is, it is just we have seen, but we will see again. Very important part here is note that register file is written to by the output of ALU as we just saw. Okay, so let us see the first part of that, the program counter. I just we consider the program counter. So in this program counter, in this program counter, as we said, program counter consists of the instruction address, that is your next instruction address. Okay, so the output of that next instruction address will be given as an input to your instruction memory, and that instruction memory that reads, so which operation is happening here in data path. In the instruction memory, upon the control signal read, it is reading the address of your instruction. That address of your instruction is, okay, that address of your instruction is identified in this memory, and the instruction will be given as an output. So that we give as you are fetching that instruction from the instruction is fetching from instruction memory. And once the instruction is fetched from your instruction memory, your program counter is going to calculate the next instruction address by adding 4 bytes. So why this 4 bytes? We consider for, in our address, if we are using the 32-bit instruction address, so this 32 bits will be represented with your 4 bytes. So if I have a program, that program is having the instructions like instruction 1, instruction 2, instruction 3, instruction 4, instruction 5. So every instruction takes 4 bytes. So the second instruction starts after 4 bytes. Third instruction starts after 8 bytes. Fourth instruction starts after the 16 bytes, and so on. So initially when it is having the program counter is having 0th address, then that is occupying 4 bytes. So to go to the next instruction, it will be added with this 0 plus your 4, it gives your 4. So that is the next location of your instruction will be calculated. So in the next case, it will store 4. Then it will add the 4 plus 4, that is add 8. That 8 will become, and it will store here. So the output of this one is 8-bit here, 8. The address of that one is 8. Address of next instruction 8 goes here, this 8 comes, so that 8 plus your 4, that is 12. So it goes on this process. So in the register file, as we just saw, you can see in this register file that when register write signal is control signal is given by the processor, as you said, it takes two inputs. One is your address, another one is write, and one output port is that is your read port. Okay, and this data memory, register file data memory, is taking two signals, register write signals. One is memory write signal and memory read signal. Memory write signal and memory read signal. When the register write signal is your memory read signal, suppose your control unit, then the read means these two ports are going to be enabled. Two input ports of your data memory enabled. Okay, but these two ports are enabled, but only one port will be activated. Only one port will be activated. Either the address will be read, or when the register write signal is given, then it enables these two address and write ports, but any one will be happening, not both. Okay, when the address read write is happening, in that case it is inactive. Write data is inactive. When write data is active, then that port is active, then this address port is inactive. And when the instruction execution time, when the clock signal or control signal gives the memory read instruction, then there is only one port that will be activated, enabled, and that read data, the actual value, the actual value will be given out. So when this output is coming out from this data memory, okay, it is in the form of your 32-bit word. 32-bit word. Okay, so in this case, the input, write data input, it takes input from the component your sign extent. Okay, in that sign extent, your input write data is with 16-bit word. 16-bit word. So this 16-bit word will be converted into 32-bit word. 32-bit word. Okay, that means what? When we have seen in the signed representation of your numbers, in signed representation, we have seen that the floating point or your the integer numbers are there. The signed representation, we use the IEEE 754 single precision. That single precision, which takes 32 bits in format, and in that 32 bit we have seen that what are the format is there. First bit is your sign bit, next 8 bits are the exponential bit, this is sign bit, exponential bit, and remaining bits are your fractional bits. So whatever the input data is coming in terms of your 16 bits, that will be converted into the extent 32 bits. So this floating point representation or 32-bit representation, there is separate component called sign extension bit. Okay, so in that, how it is extending, that means if you are having a 16-bit like this form, then the most significant bits will be replaced with all ones. Means the remaining 16 bits represent with all ones. This position. Okay, so this 32-bit output of your signed extension is given as an input to your data memory to write this data into the data memory. Okay, so that is what we observed in this case. The signed extended output will be given as an input to perform the ALU operation, as well as that address will be given to your data memory. That address will be given to your data memory. as an input. Right? So this is the functionality of your data memory. Remember, when this write signal is activated, then it enables these two ports, but only one port will be able to work. Another port will be in idle mode. But whereas if read instruction is given, only one port, so the output of your data memory will be converted from 16-bit word to your 32-bit word by using your sign extend element. So let us consider one example for your R format or register format data path implementation. Register format, or we can say that the arithmetic and logic operations, the arithmetic and logic instructions, we also called as your R format data path. So the implementation of this R format data path implementation. So this implementation of data path, that is R format instruction. That means what are those instructions? Add, your subtraction, your AND, your OR, and set less than. These instructions in our examples we are taking. Okay. So this R format instructions is fairly straightforward. The register file and the ALU are all that is required to perform this one. So this ALU accepts two inputs, the arithmetic logic unit. This accepts two inputs and one output. What are those inputs? These inputs are the registers only. Your register source 1 and your register source 2, and the result will be go and store in register destination itself. So the ALU accepts the inputs from your data read ports, from where here is your register file. That register file is giving the output of this one is the read of your read port of your, the output of your register file, we can say the read port, data read port, and that will be given as an input to your ALU. So that is data read ports of the register file, and the register file is written to by your ALU. The output of this one will go and write in the write port, as we saw in the previous diagram, the write port, the result. Okay. So see here, the same thing is explained. Let us consider this example. The operation which I had is R1 is equal to your R2 plus your R3. Consider the same example, like R2 is having 5 and your R3 is holding the value, data value is 6. R2 is holding data value 5 and R3 is holding data value 6. So this operation is written in this format in the instruction code. Okay, so that instruction code is opcode and the format is opcode and your registers. So what is our opcode here? Okay, so the opcode says that your operation code is equal to your add code. Your source 1 is equal to the source 1 is equal to your R2. Your source 2 is equal to your R3. Your destination is equal to your R1. Okay. So when the program counter gives the input, the output of your program counter given as an input to your instruction memory, this instruction memory is holding the instruction that add, you can write here, add your R1, R2 and R3. For add, suppose the 3-bit representation in binary is 0, 0, 1, For R1 it is 0, 0, 1. R2 it is 0, 1, 0. R3 it is 0, 1, 1. So this instruction, arithmetic operation instruction, will be available in the instruction memory. So the output of this instruction memory will be this one. So from this instruction, it is decoding. When it is decoding, then in the decoding phase only the register file is there. So these three registers are identified. When this 001, 001, the output of your instruction memory, that is 001, is given as an input to your register file, by this 001, this is the identification of your register in register file that will be added. So which port? The read port, the read port of your register file, it will be taken this address, the address of your register 1. So register 1 is taken. So that is for destination. And second one is, it takes the next part is your 010, that is your operand 1, that is R2. Okay, and it takes this operand, this is 001, this is 010, this is 011. So when it is taking 001 means your right operation, that is R1, 010 means R2, 011 means R3. So read operation is done. Okay, so then the output of your register file, what it says, it must give then it gives the instruction that, read operation instruction. The control signal gives the read operation from this register file. So the output of the register file is from this R3. The first one is your operand 1, right? The read data 1. So R2 value, that is R2 is equal to here 5, first data. So that is 5 will come the output, that the data will come out of your register file 1. And second operand is your R3, that is holding the value 6. The output of your register file is 6. So ALU is taking the input for this ALU are registers only. First operand and second operand, both are registers only. So in ALU, it is a register and ALU only. All arithmetic operations can be performed with registers only. So that is, it takes two inputs from these two register and it will add this, and we have 5. First operand is there and second operand is there. Now, which operation this arithmetic and logic unit should perform? So the control unit will give the instruction. Control unit will give the inputs, the control signal to ALU. What is the control signal? The ALU signal will giving. The control signal is, we are considering only 4 inputs here, right? One is 4 operations, ALU operations. What are those? One is add operation. Another one is subtraction operation. Another one is your AND operation. Another one is your OR operation. Another one is SLT. So to represent these operations, it takes 3 bits. Okay, so that is 0, 0. Let us consider 1, 0, 0, 2 for subtraction, 0, 1, 0 for your subtraction, 0, 1, 1 for your AND. For OR, you can write 1, 0, 0. And for slot, you can write 1, 0, 1. So this ALU, the control, it sends the control signal in terms of 3 bits. This control signal gives, the 3 lines will be there here. Here the slash is used, that is having the parallel lines. So ALU gives these 3 signals 0, 0, 1. So first input is 0, second input is 0, third input is 1. Then with this, it identifies the control signals, informs or gives the direction to the ALU that perform the addition operation. So then it performs the addition operation of this. So 5 plus 6 will be added, and the result of this one will be your 11. So now this 11 is a data. 11 is a data. Okay, and where this 11 should go and write when the instruction is decoded. When the instruction is decoded, it is given the signal, that control signal, that the result will go and store in the R1 register. So this data will come, this data, okay, this 11 data will come, okay, and then the control signal goes, the register write signal will be activated. When this write signal is enabled, then this port will be enabled, that write data port will be enabled, and that writes the 11 into your register. Okay, so where it should go and write, it should go and write in the register, it should go and write this data into the register R1. So that is, it is going to write in R1. So this is the data path of your R format instruction data path, or we call this arithmetic and logic unit data path. Arithmetic and logic unit data path. Okay, so then this next class of instruction is your memory reference. Sorry, the next class of one is your memory reference instruction class. Memory reference instruction class of your millions of instruction per second part. Okay, so this, we would like to stop this session here. We will try to discuss this in the the next class.